So here we're going to take a look at, we're in the section of vectors. And today we're going to take a look at vector operations, the section that we'll be covering. All right, so section VO. And we'll start off with a definition. All right, so the definition here is the vector space of column vectors. So here's our first introduction into this idea of a vector space. We will go more in depth in a later section once we introduce some other objects that we'll be working with, like matrices and whatnot. But for now, here we'll take a look at this vector space, specifically of column vectors, and we'll look at the properties that define a vector space. But first, the definition of what, when we say vector, as we've seen, vectors can mean a lot of different things, right? It can mean geometrically and physically what they mean here, but in this specific context, in this class, they'll take on a whole new meaning of objects that we call vectors, right? But we start off with a basic vector here that we call CM. So the vector space CM is the set of all column vectors of size M with entries from the set of complex numbers C. Now, throughout the book, the author makes note of the complex numbers as being the field, the set where we derive all our values from. Now, in general, really, I refer to the real numbers, right? So we won't really worry too much about any complex numbers. So really, the vector space that we'll be looking at is this Rm, right? And we call this Euclidean M space. Okay, so here, so the values don't come from the complex numbers Cn, they come from the field of real numbers. Now, the author also uses the word set, but really we can define the real numbers as much more than a set, right? It is a field of numbers with its own properties, which I'll go over in the following video. The purpose here is to simply define, first of all, what a column vector is and get comfortable with the notation, right? So here, instead of the complex number C, we're going to be looking at R to the M, and then the entries come from R, right? The real numbers, right? Entries from R. Okay, so we define a column vector. So if we say UV is the element of R to the M, right? So a couple things on notation, right? I use this like arrow over the U and the V. Our textbook uses the boldface to define what a vector is, right? So those are equivalent, right? It's just kind of harder here to make a bold typeface stand out. So I use the arrow notation here, right? So here, UV being just general vectors in R to the M, the vector U is a column vector. So the values look like this: U1, U2, etc., U, M. And then V is the vector V1, V2, V sub M. All right, where here, these U sub i's are an element of the real numbers, where I is the subscript less than or equal to M. Right, and the same thing here, right? The V sub i's are the element of the real numbers, where 1 less than or equal to I, less than or equal to M. Okay, so again here, what would be a good use of our study time is we get comfortable with the notation, with the definitions, because they're just going to keep coming. A lot of this class does have a lot of just notation, definitions that are vocabulary that's just kind of important, and we need to be able to talk in this new vocabulary, right? People usually say math is can be thought of like another language, and it's not more evident in this linear algebra class. Right, so we got to be comfortable with using the notation as long as well as with the vocabulary. All right. Now, when working with these vectors, sometimes I just want to refer to an element in them. All right. Now, a general way to do this is this notation here, where we use these brackets and we use u, the vector u, I. So this is to make note that we are referring to the ith term here. Okay, so if let's say, for example, that my vector u came from the R3 space and it looked like this, it looks something like this, right? Then we would say something like u3 is equal to 1, right? So again, here, these are ordered, right? So the order of it does matter here, okay? So we use this to define an entry in there, right? So we do want to make sure that we understand the difference when I use in a sentence or in a proof, this is different than this, right? This is an element of R3, or we'll just keep it general, Rm, while as this is an element of the real numbers. Okay, all right. So now as we see, while it may seem almost obvious when we define terms like equality or or addition and scalar multiplication, I think it's important to note that here when we're thinking of the real numbers, right? Those properties, right? I know what this means, right? I know for instance these statements, right? Those are kind of the axioms of the of the real numbers, right? But here I want to define what it means for column vectors to be equal. Define column vector equality. Okay, so we suppose u and v are an element of R to the m, then u and v are equal if, and by equal, I use this notation, right? Now again, here one thing to also keep in mind, so they're equal if, and I'll state that in a second, we kind of are reusing this same equal sign, but notice that the equal sign up here where we have 1 equals to 1 is not the same as the equal sign here, right? Here we're going to define what it means for the equality to be true here, okay? So if you guys ever done any programming, right, we have this idea of overloading an operator, and that's kind of what we're doing here, right? You gotta gotta pay attention to all the details here, right? So when we say equality here of vectors, what does that mean? Well, this is what it means, right? And again, it comes from the definition up here, right, from this property, right? What we're going to define for two vectors to be equal is we define that each of their elements is equal to each other. And this has to be true for all I. All right. So that's what we're going to define to be vector equality. Okay. All right. Okay. And again, right, these are all their foundations, right? It's necessary to make sure that we write these out because as we'll see later, we can define this idea of equality to be different things, right? So for this particular case, this is what we mean when vectors from R to the m are equal, right? And also, as we can see here, we can start start to think of even like a system of equations, right? The idea behind this is, okay, now that we have these column vectors, we can start thinking of like even our systems that we've been working with, right? We've talked about them as three simultaneous equations, or however m simultaneous equations that we solve simultaneously. Right? But now we can start pulling away from that idea, right? And instead of having these as like three separate things, we can think of this as the column vector and then x1 plus 4x3, 24, 5. Okay, and we can start think about it like this, right? Where now we hear, well, instead of having these three equal signs, we have one equality here, where we have a vector equal to another column vector, right? And now I can do that, and I know what vector equality is, right? Each element is equal, right? The first element is equal to the first element, and etc. All right. Now this is just kind of a very trivial example here. We'll go further on this type of ideas when we're talking about different these column vectors and any other type of vectors that we'll define throughout the course here.